How's it going? We have officially learned all four different conic sections. We've done the circles, parabolas, ellipses, hyperbolas. Today, what we're going to do is we're going to look at all four of them together, but in a different form. We're going to look at general form for all these conic sections. Sometimes general form is a better form to work with. Sometimes the standard form that we've been using is better. Standard form is great for graphing. General form is going to be better for doing some algebra. All right, so here we go. This is what general form looks like. Now, this looks long and scary. There's a lot going on. This really works for all four conics. It just kind of different. The A, B, C, D, E, F are the coefficients, and they'll be different depending on which conic we're dealing with. But you'll notice that we have an x squared term and a y squared term. We have just a linear x and y term, and then we have a constant. Now, you might wonder where the c is. The c is the coefficient of the x times y, so it'd be cxy. But we won't really deal with that term, so I've left it out of there. Now, for some reason, this quick snapshot got cut off, so I'm going to tweak it. Your notes probably have it, but when you're trying to decide, when you're looking at a conic that's in general form, which conic is it? Well, if it's a parabola, then A or B is going to have to be equal to 0. And really what that means is there's only going to be one of these terms one of these terms squared. So think about it. A parabola, we know it's like a y equals x squared. So there'd only be an x squared. But if it was one of the sideways parabolas, then you'd have an x equals y squared. So the a wouldn't be there, meaning the whole term would be gone and you'd only have a y squared. So if you want to tweak this, officially a or b is 0. You might notate there is only one squared term. That's really what you're kind of looking for. Okie doke. Now, if it's going to be a circle, both of the squared terms are there, but the a and the b will be equivalent. Oftentimes, they're both 1, but they can be fancier than that. Maybe they're both 2 or 4 or something like that. An ellipse will have both the x squared and the y squared, and your a and your b are going to be the same sign, usually both positive. All right, and then that takes me to the hyperbola, which is very similar to the ellipse. Think about how their standard form equations are. They're almost identical, except that in the hyperbola, remember that you do subtraction. And so A and B are going to end up being different signs. All right, so that's the 4 things. Now what I'm going to do is I'm going to throw a bunch of equations at you and see if you can identify which conic they are. All right, so I've got 6 examples for us. I'm going to do 3, then you're going to do 3. Let's start with this first one. When I'm looking at this, I notice that both squared terms are there. So I know it's not going to be that parabola. And then I look at the coefficients and I notice that they are different. So that's the sure sign that's going to be an ellipse. All right, let's look at number 2. Again, both squared terms are there, but this time the coefficients are both 1. They're both the same. All right, so that's going to end up, ultimately what that's going to force happening is from the center, you're going to go left and right the same as you go up and down. So that's going to make you have a circle instead of an ellipse. All right, let's look at number 3. I just do a quick scan. Do you notice there's only a y squared here? There is no x squared. Guarantee that's going to be a parabola. Only one squared term. All right, now take a moment, go ahead and pause this video and you do the next 3 on your own. Come back when you've got it. All right, here we go. Number 4, you should have an ellipse on that one. You have both squared terms there, but they have different coefficients. That's going to make you go left and right differently than you're going to go up and down. All right, number 5, the big thing that jumps out here. Yes, both squared terms are there, but you have a subtraction going on. So if these are different signs, now we've got ourselves a hyperbola. And number 6, both squared terms are there. Got the same coefficient though, so I'm going to be going left and right the same as I go up and down. That is a circle. All right, so that's going to be the key thing that you do first, that you can identify what you're looking at. After that, we'll then keep moving. And what we're going to practice today is getting this put back into standard form so that I could graph it if I wanted to. To do this, to switch from this general form to standard form, now this says for a circle, but this is going to be the case every time, we must complete the square. That's how you're going to get it into the other format. So that's what we're going to be doing a bunch of today, completing the square. What you're trying to do is, if you think of it in standard form, now this one's going to be a circle. And remember the circle format. I'm going to write it up here. It would be an x minus h squared plus y minus k squared equals r squared. We're trying to get it into this format. So when we say complete the square, what that means is you're going to be creating a trinomial that's going to factor to a perfect square trinomial, which is going to look like this when I factor it. So that's all of the conics have this format where you have this quantity squared. That's what we're trying to get. So to do that, in this first one, I'm going to group my x's together. So instead of having the x squared followed up by the y squared, I'm going to rearrange. I'm going to say x squared, then I'm going to put my minus 8x plus, and then I put a blank because I'm going to complete the square. I'm going to put a number there that will complete the square. Plus y squared plus 6y. And you'll notice in our equation of our circle that we want the radius squared on the other side. That's going to be just a number. So that 9 right there, I'm going to move him over to the other side. Okay, so now let's complete the square. We have to come up with a number here that will go into this blank that will create a nice trinomial. You don't really need to put these parentheses, but that's kind of what we're doing. Creating this trinomial that will factor to my binomial squared. So to do that, if you'll recall, you take your b value here, the coefficient on your x, you're going to take half of that and then square it. So half of 8 is 4, squared is 16. But if I put a 16 randomly here on the left side of the equation, I've got to put a plus 16 on the right side to keep it balanced. Then I'm going to do it again. I do it with the y's. Half of 6 is 3, squared is 9. So if I'm going to put a plus 9 there, again, I'm just going to do these parentheses, but I probably won't ever do that again. Put a 9 there, got to put a 9 on the other side. What we've managed to do is create this nice trinomial that's going to factor as this binomial squared. This will factor to x. Keep that sign minus, and it's going to be a 4, because that's what you squared to get the 16. Plus, now let's do it with the y's. It's going to be a y. You always keep this same sign. So this was a minus, this is a plus, and the number I squared was a 3. Equals, and now I can kind of clean up this other side. The 9s actually are going to cancel, and I'm going to have a 16. And I am done right here. This is my equation of a circle in standard form. Now I do want to graph it. So the center you should now see. Remember, inside the parentheses, you're going to do the opposite. So the center is going to be a 4, negative 3. The equation is always equal to your radius squared. So 16 is my radius squared, so my radius must be 4. And just as a quick review, remember the eccentricity kind of tells you how round the conic is, and a circle is very, very round. Eccentricity is always 0 on a circle. Let's go ahead and do a quick graph. Over 4, down 3, there's the center of my circle. Since I have a radius of 4, I'm going to go left, right, up, down, 4 units, and then make a nice curvy round circle. And there we go. There it is. All right, so I'm going to do one of each. That was a circle. The next conic we're going to do is a parabola. So to convert from general form to standard form, we must complete the square. All right, now what's different, though, on a parabola, since there is only one squared term on a parabola, we'll only be completing the square once. Sometimes you'll do it with the x, sometimes you'll do it with the y, depending on whether it's one of those sideways parabolas or up and down. When I look at this equation, the y is what's being squared, and so the y is what I'll be completing the square with. So here I go. I'm going to write y squared plus 4y plus something. And then there's different ways that you can do this, and we may have collaborated in class and came up with a strategy. I'm going to go ahead and I'm going to move the other stuff to the other side. I'm going to subtract the 6x and I'm going to add the 2. Now I'm going to finish up completing the square. Half of 4 squared is going to be another 4. So by putting a plus 4 there, I got to put a plus 4 on the other side. So now here's what I've got. Y plus 2 squared equals, and then this is a negative 6x plus 6. Now, let's think about what we're shooting for here. I want it to look like this. I can see that the y is the squared term, so it's going to look like this. X equals a y minus k squared plus h. That's the format that I want. So what I can see right here, I've got that quantity squared. I don't really have an a value on it, and my x is not really isolated yet. And so really that's what I need to do. I need to isolate that x. So the first thing I'm going to do is I'm going to take this 6 that I have back over to the other side. So now I have a y plus 2 squared minus 6. And I'm going to do this over here. I'm going to get my x. Well, no, I'm not. All right, so then your next step would be to divide by this negative 6. Now, this is a little bit weird, but you're dividing this by negative 6 and you're dividing this by negative 6. You got to take each part and divide it by negative 6. Now my x is isolated, and just so that it'll look more like this, I'm going to go ahead and put my x on the left side because it's now isolated. So I have x equals. The next thing you kind of need to recognize is this divide by negative 6 right here on my quantity. That's really the a value. But a is really what we're multiplying by. So I wouldn't really write it as a divide by negative 6. Dividing by negative 6 is the same as multiplying by a negative 1/6. That's what your a value becomes, negative 1/6. And then I have this quantity squared, and then that's actually going to turn into a plus 1. That came out really nice for us. All right, so now that we have our equation written, now we can find all the parts, and then from here on, it's really review of what we've done here the past few days, because I've got it now in standard form. The vertex is going to come from this value and this value, but notice that it's an x equals. This is one of those sideways parabolas, and because it's negative, it's going to open towards the left. But really what I wanted to draw your attention to is this right here is with your y. This is a vertical value. So when you write your vertex, I'm coming up here to fill in this information. Your vertex is actually going to be that minus, that negative 2, because it's a plus and you always do the opposite, is really your y value. Your x value is coming from out here, and it's a plus 1. So the vertex on my parabola is 1, negative 2. Going to graph it. I'm gonna find these 4 things, but maybe not in this exact order. I know that it's going to open to the left. We've already acknowledged that. Now, what's a little bit weird is my a value is a negative 1/6. So if I want to graph this, and I'm going to graph sideways, remember that how we've done this is we sort of just turn our paper sideways and treat it like an up and down parabola. Hard for me to turn it here, so I might just turn my head and think sideways. But ultimately, you're thinking of your parent table for a parabola. Normally would be 1, 1, 2, 4, 3, 9. I'm going to keep going. 4, 16. You know what would be a good one to have? Is maybe a 6, 36. Well, let's see how that plays out. We'll see. Okay, so what I have to do is I have to take all of these times 1/6 because that's the A value. And actually, it's a negative 1/6. And I'm just trying to get the gist of this. I know that this is a backwards scenario because you're going sideways. So this really is not like that, except that's how we've kind of just simplified this process, is just think of it as an up and down parabola, but you're going to graph it sideways. So I'm turning my tablet right now. I'm turning it so I look at it. I know you can't tell I'm doing that, but here I go. So instead of going 1, 1, I'm going to go 1, 1, 6. Okay, that's hardly worth graphing. I can't even figure that out. So I'm going to go down a little bit farther. In fact, I might go clear to the 6, 36. Instead of going over 6 up 36, I'm going to go 6 and 1/6 of that. So that's going to be 6, 6. So let's see where that would fall. 1, 2, 3, 4, 5, 6. So it's right here. 1, 2, 3, 4, 5, 6, right there. Okie doke. Oh, already lost track of where I was. Right. There's my dot. Okay, that works out okay. Going the other way, ran a little bit out of room, but I can make it happen. I feel like those are going to get me a better feel than any of these other points, and I'm just going to try to make this nice and round looking like a parabola would. Okay, so there's my graph. My axis of symmetry is going to cut right through the middle of that thing. I usually don't graph the axis of symmetry because my graph starts getting really messy, but there it is right there. And that's a horizontal line. So it's going to be a y equals, looks like -2. Remember that that's really going to always match what your vertex is because your axis of symmetry goes through the vertex. Now, for your focus and directrix, you have to figure out the p value. The p value, remember we have a couple rules and you can use whichever one helps you the most. You can do an a equals 1 over 4p. You could also do p. Oops, let's do a colon, one of these. I don't know. Really, I don't want anything there. Never mind. Oh, it's a big bar now. Okay. A equals 1 over 4p or p equals 1 over 4a. The thing is I have the equation, so I know what the a value is. This is a pretty ugly one. I'm going to be honest. Good thing this is kind of review for us because having an a value of 1/6 isn't going to work very nice in either of these scenarios. Now, you could put a 1/6 right here, and I know it's really a negative 1/6. Negative 1/6 equals 1 over 4p, and you could do cross products on that. Or you could come over here and say p equals 1 over 4 times negative 1/6. Well, heck, that's a mess too. I'm going to go back to my cross products. I'm going to end up with a negative 4p equals 6, divide by -4, and I end up with a -3/2. So if your p distance is 3/2, that's the same as 1.5. So that means my focus is going to fall right here, where it's 1.5 units from the vertex. My directrix is going to be on the other side. It's going to be a vertical line 1.5 units away from the vertex. All right, so the directrix is a vertical line, so it's going to be an x equals, and it looks like that would be at 2.5. And my focus, if I were to go left from the vertex 1.5, that ordered pair would end up being a -1/2, -2. All right, I sometimes think the parabolas are maybe the hardest one of all of them to do. All right, let's keep moving. That one took us a little while. Next conic we're going to look at is an ellipse. So to convert from general form to standard form, guess what we have to do? Yes, we have to complete the square. Now, this one's going to be harder because when we complete the square, we're not allowed to have a coefficient on our squared term. So this is how we're going to play this out. I'm going to go ahead and group my x terms together. So I'm kind of thinking it like this, but I'm not allowed to have that 9. So what I end up having to do is factor the 9 out like this. Then I'm going to complete the square. Now let's try it with the y's. I would have a 4y squared plus a 16y. Remember that we're going to want that 11 over there on the other side. So I'm going to add it over here. But really, I'm not allowed to do what I have there. I have to have this coefficient on y squared be a 1. So I'm going to factor a 4 out. All right, so now let's go ahead and complete the square. So I look at this 2, take half of 2 and square it. It doesn't really even matter that it's a negative because when I square it, it's always going to make this be a plus sign. So half of 2 is 1 squared 1. Put a 1 here. But if you recall when we first did completing this square, when I put this 1 here, this 1 is getting multiplied by a 9 when I stick a 1 right there. So by putting that 1 there, what I really put was a 9. So I do a plus 9 on the other side. Now let's try it with the y's. Half of 4 is 2, squared back to a 4. But when I put that 4 there, I really put 16 there. So let's add 16 to the other side. Here's what I've got. 9. This is going to factor to x minus 1 squared plus 4. This is going to factor to y plus 2 squared equals, what are we going to end up with over here? We've got a 27, 36. Okay, now here's the thing. Do you remember what an ellipse equation looks like? It doesn't look like that. It looks like this, x minus h squared over a squared. It's always a plus sign there. Then we had a y minus k squared, put it over b squared. Remember, a and b can swap, but don't get caught up on that. It always equals 1. That's what I'm trying to turn this into. I can't have a 36 here. I need this to be a 1. So there's 2 ways to make it be a 1. I could either subtract 35. That's not going to play out very nice. What I'd rather do is divide by 36. If I divide everything by 36, look how awesome this is going to play out. Yes, I'm going to get the 1 that I want. Yeah, but look, the other thing that ellipses don't really have here is they don't have a coefficient out on front, and I do have a coefficient. But by dividing by that 36, looky, that's going to divide out. And it's going to divide out here. And we got super lucky to have both of those divide nicely. Well, okay, you just have a really nice teacher. That's what it is. Because they don't have to be that nice, but I'm going to make them be nice. So this 9 will reduce, and that's going to turn 4. That 4 is going to reduce. That's going to be a 9. So finally, x minus 1 squared over 4 plus y plus 2. 9 equals 1. That is my equation. Now let's go ahead and graph this. The center comes from your numerator. It's going to be a 1, negative 2. And then my denominators tell me how far to move left and right. So remember, this is the a squared. So I'm going to move left and right 2, up and down 3. Make a nice oval, not pointy. I would have liked that to be a little bit more up there. Okay. Now, I also want to find my foci. So your foci, since this is a tall ellipse, your foci are going to be up and down. Now, remember, I kind of purposely don't stick those foci on a grid line because I don't want you thinking that they fit in there perfectly. And then we create this triangle. And ultimately, I'm looking for the coordinates of that focus. I'm wondering how far up to go. That's going to be my x. I know how far I went left and right. I know that's a 2. And remember that your hypotenuse is always the same as that longer distance. So that longer, that semi-major is 3 units. That's what the hypotenuse is going to be. Also 3 units. If I do Pythagorean theorem, I'm going to have x squared plus 2 squared equals 3 squared. That's a 9 minus 4. X is going to be square root of 5. What that means is from the center, I'm going to go up square root of 5, but I'm also going to go down square root of 5. Notice that is affecting my y values. So when I write my foci, I'm going to affect the y value of the center. I'm going to be looking at this -2. So the 1 is still going to be there. But now my y value is going to be -2 plus or minus that root 5 value. Last thing, eccentricity. Remember, that tells you how round your ellipse is. And the closer your focus gets to the edge, the closer to 1 we get. And the closer that focus gets to the center, the more circular it gets. Let's see what we end up with. Eccentricity formula is C over A. C is always the distance to the focus, which I know is the square root of 5. And A is always the semi-major. And in this case, that's a 3. And then we could go ahead and divide that out so you get a better feel for what that value is for an eccentricity. So square root of 5 divided by the 3, and I got a 0.75, let's say. So eccentricity would be 0.75. All right, we have the hyperbola left. Let's go look at that. All right, so works very similarly to the ellipse. We have this coefficient that we're going to have to deal with when we complete the square. We do have a minus sign here, and that is going to change some things up. Let's go ahead and get going. I'm going to group my x's. So 4x squared, it has a minus 8x. I'm going to be completing the square. And then it's a minus y squared plus 4y. Going to be completing the square. Going to move that minus 8 to the other side. Now, I want that coefficient, that leading coefficient, to be a 1. So I'm going to factor out the 4. Oh, look how nice I am. Again, divides nicely. Won't always have to be that way. And then I'm going to complete the square. Half of 2 is 1. Squared is 1. But when I put that 1 there, I really put a plus 4. So let's put plus 4 on the other side. Now we're going to do this again. This is a -1 ultimately that I have to factor out on this because I don't want that leading coefficient to be even a negative. So I'm going to factor out a -1. Gets me a y squared minus 4y. Half of 4 squared is a plus 4. But when I put the plus 4 here, I really put a minus 4. So I have to put a minus 4 on that one. So the 4's happen to conveniently cancel out, and I'm back to 8. I'm going to go ahead and clean this up so it looks like a binomial squared. So this is going to be x minus 1 squared. And then here's where that minus sign is going to come into play. It's going to be a minus and then a y minus 2 squared equals 8. Just like with the ellipses, I don't want it to equal 8. I want it to equal 1. So I'm going to divide by 8. The 4 over 8 will reduce. So that's going to become x minus 1 squared over 2. Not really very pretty there. Next one's going to be a minus. And this one, it doesn't really have any reducing to do. It just is what it is. But it does equal 1 now. Now that this hyperbola is not really our easiest one we've ever done, but this is the second day of going through it, so we are going to amp up the difficulty level. So first, let's plot our center. It's going to be at 1, 2. All right, that's the center of the hyperbola. And then look at what you're doing to create the box. This is how much you're going left and right, but not 2. Remember, it's the square root of this number. So I have to go left and right the square root of 2. The square root of 2 happens to be about a 1.4, so I'm just estimating that in there. Okay, the next one, I have to go up and down the square root of 8. The square root of 8 would be really, really close to the square root of 9. So it's going to be pretty close to 3, but not quite, like a 2.8. So I'm going to go up and down 2.8, something like this. Now I'm going to draw the box that is created from that. I'm going to draw in the diagonals. And then we have to decide, do you feel like this is going to open up and down, or is it going to open left and right? Has to do with which term is the positive term. You can see that the x term is the positive term, y is the negative. So since x is positive, it's going to open to the sides. So here's what my hyperbola would look like. Remember, it just hits that side of the box there. Those are considered vertices. Now, I'm going to draw the triangle that gets created. If you will recall, and we just did hyperbolas, so hopefully you do, but the foci are in the cup of the hyperbola, so they're like out here somewhere. Now, I'm kind of exaggerating it. They're probably not really that far away, but they're out there in the cup of the hyperbola. But they're outside of that box. When we draw the triangle, we always draw the smaller version. So when I go over here, I'm going to stop when I get to the vertex. Don't go clear out there to the focus. Stop when you get to the vertex. So here's my triangle. And that hypotenuse is always the same as that farther distance. So that hypotenuse is really what I'm looking for because it's going to tell me how far out there those foci are. So I'm going to redraw that triangle a little bit bigger over here on the side so you can see it better. I know to build that box that I went left and right the square root of 2, and I went up and down the square root of 8. What I really want to know is what's that hypotenuse. So Pythagorean theorem, square root of 8 squared plus square root of 2 squared equals x squared. So you've got an 8 plus 2, that's a 10. Was hoping this was going to come out nice. It didn't. That's okay. So x is going to be the square root of 10. That x is this hypotenuse. It is always also that farther distance out to the focus. So from the center, I'm going to go right and I'm going to go left the square root of 10. That's affecting my x value because I'm moving left and right. So when I write the coordinates for the foci, the x started off at a 1. That's where the center was. But then I added and subtracted the square root of 10. The y value is the same as the center. It didn't move up and down at all, so it's going to still just be at 2. Next thing will be our asymptotes. The asymptotes, I'm going to make those, well, I have the asymptotes drawn, but what I want to do is I want to write the equation of them. So remember that we always do this in point slope form because it always goes through the center point, and that's easy to work with. And then the slope is always going to be a positive version because I'm going to get to this corner of the box, or the negative version that's going to go to that corner of the box. So in point slope form, it goes y minus the y value of your center equals m, but remember we do it with a plus or minus. So I went up, that's this measurement here, I went up the square root of 8, and I went over the square root of 2. So plus or minus the square root of 8. Okay, I'm going to do a little side note. Square root of 8 over the square root of 2 would really just reduce to the square root of 4, which would really just reduce to 2. So here finally something's going to come out nice for us. All right, our slope, plus or minus 2, and then x minus the x value of our center, which looks like this. Last thing, eccentricity is c over a. C is the distance to the focus. The distance to the focus was this distance, which was really the same as that hypotenuse that we went through all this work to find, right there, square root of 10. That's your C value. Your A value is how far out to the vertex, so to right there. That distance was square root of 2. So C over A, square root of 10 over the square root of 2, which is ultimately just going to end up being the square root of 5. Good. I guess I'll write that here. You could write square root of 10 over the square root of 2. That is going to be the square root of 5. I would like a quick decimal on that. So square root of 5 is 2.24. Remember that it will be bigger than 1 always. All right, those problems take a little bit, no doubt about it. But also hopefully you'll get a little bit faster because it's starting to be review for you. Now tomorrow is going to be an application day, and that's all we're doing is a whole bunch of applications. So I'm going to give you a little preview so you see what's coming. This isn't easy stuff anymore. We're hitting the near end of this course, so you're going to come across some tough problems. It's time to double down. Here's our problem. I've got a football stadium that it's going to be built so that the stands are 2 concentric ellipses. So you can see the shaded part is going to be where all the stands are. And the inner ellipse is kind of like the field. But all the ground, so the teams are going to be on the sidelines and stuff here. But then the rectangle is the actual playing field. They give us all the dimensions that we're going to need. And they tell us what the dimensions of the outer ellipse are and the inner ellipse and the football field, everything. All right, so we have several things we're going to have to find here. Find the standard form of the equations of the inner and outer ellipses. All right, this is probably going to be the easiest part. We have to find the equations of the ellipses. But we're going to make our life simple. We're going to let them be centered at the origin. So for my let's go ahead and start with which one did they talk about first? The outer ellipse. Okay, so let's work on the outer ellipse. I know, I mean, there's so much of this equation you can write without too much thought. So don't ever leave it blank. You know it's going to be an x squared, it's going to be a y squared. You know it's a plus sign. You know it's a fraction. You know it equals 1. All of that. Very straightforward. Now I have to use my dimensions. It says that the outer ellipse is to be 240 yards long and 200 wide. So I'm going 240 this way. So if the whole thing is 240, from the center, it would only be 120. And so remember, that's what you put in your denominator is how far you're going left and right from the center. So this is going to be 120 squared. Then it tells me that I'm going to be going, it's 200 wide. So that means from here, the whole thing is 200. From the center, I'd be going up and down 100. So my denominator is 100 squared. Now you can multiply those out. It'd be fine. I'm going to leave it like that for now. Okay. Now what I want you to do is the same thing, but I want you to do the inner ellipse. All right, take a moment to pause the video and go write your equation for your inner ellipse. All right, take a look at my equation, see if you agree. If so, let's keep moving. So the next part is really going to be the good part here, where you can see a use of even knowing what these equations are, how those are helpful. We want to know how much clearance there is going to be between the field and the inner ellipse at this corner point A. In other words, how much walking distance would we have? Could we get a little gator through there? How much space is there? And we're talking straight north. So straight north, not at an angle, but straight north here. How much space is there? So I already give you a hint. It's just like we did with the circles on that first day. It says find the difference of the y values of the point and the ellipse. So I'm going to have to find a coordinate right here due straight north, that coordinate right there, I need to know what that is on my inner ellipse. Remember that your equation on your inner ellipse is the set of all points that will land on this circle. So that coordinate right there should fit for x and y. Now, let's look at the dimensions. We should be able to tell what this coordinate here is for A, and that should help us work on the coordinates for B. So A is the corner of our football field. So the corner of the football field is 120 yards, because that's including your end zones, 120 yards by 160 feet. Okay, that's a little bit problematic to have that in feet when everything else is in yards. So what I'm going to have to do is I'm going to have to take my 160 and divide it by 3 to see how many yards it is. Now, it'd be great if it came out nice. It doesn't. All right, so instead of using the 160 feet, I'm going to be using 53.3 repeating. And so anytime I use it, I'm going to hit a bunch of threes or just go grab this number. All right, so thinking about that, the 120 yards is this full length. So from the center, I'd be going left 60 yards. Good. Okay, so the coordinates of that point on point A, the coordinates of point A, I'm going to write it down here so it's right handy for us, would be left 60. And then how far up would it be? Well, from the center, I'm going, well, the whole distance is 53.3 repeating, but from the center, I'd only be going up half of that. So now I have to take the 53.3 repeating and divide it by 2, and I get 26.6 repeating. All right, those are the coordinates of A. Now what I want are the coordinates of this point that lands on the inner ellipse. Well, you should know one of those coordinates just by looking at the picture. And hopefully you're catching on that, oh, the point A was left 60, so is this point. It's left 60. I need to find the y value for it. And since it's an ordered pair that's on the ellipse, it's supposed to work in this equation right here. So I can take my negative 60, plug it in for x, and go solve this equation for y. So that's what I'm going to go do. The x is negative 60, so it's negative 60 squared over 100 squared. There's no reducing really that we're going to mess with doing on that. I'm looking for the y divided by 50 squared equals 1. All right, so now I'm going to solve for this y value right here. So just simplifying this negative 60 squared divided by 100 squared, that gets me a 0.36. I'll take that over to the other side. So subtract 1. So now I have I don't have much room here. Divided by 50 squared. 1 minus 0.36 is going to be a 0.64. Multiply that times the 50 squared. And then square root both sides. All right, I get a plus or minus 40. Now that makes sense that it's a plus or minus because I could have gone from the center left 60 and up 40, or I could have gone left 60 and down 40. But either way, 40 is a pretty nice answer there. So what that means is this ordered pair right here, I don't know if I can erase at this stage. Oh, I can erase. Okay. So what that really is then is negative 60, 40. Now, to find that distance, how much space there is to walk in between the edge of the field and where the stands are going to start. What this space is really just that vertical distance. Notice that this ordered pair and this ordered pair both have the same x value, so I don't really need to do the distance formula. I just need to figure out, well, if I'm at 26.6 and I'm going to go up to 40, how far is that? So all I'm doing is finding the difference of those. And I'm getting 13.3 repeating. So the answer to part 2 there would be then How much clearance is there? Okay, how much clearance is there? There is 13.3 repeating yards of clearance. And maybe I should write where we found that, because we do this problem enough that you're doing a 40 minus 26.6 repeating there. Okay, let's keep going. I ran out of room on that last slide, so I'm going to go ahead and get us a new slide, but might have to reference back to that picture a little bit. So it says the formula for the area of an ellipse is given below. It's actually a very simple little formula for the area of an ellipse. Remember, pi is just pi. A is going to be your semi-major axis. B is your semi-minor axis. So in other words, how far you go left and right and how far you go up and down. So let's find to the nearest square yard what the area of the stands is. The area of the stands is all that shaded region. Okay, now there's a little bit involved here, because the shaded region actually would be finding the area of the big ellipse, but then you have to subtract out the little ellipse because it's not shaded inside there. So that's what I'm going to do, a little subtraction problem. So the big ellipse is pi times how far you went left and right and how far you went up and down. For the big ellipse, that was a 120 and a 100. Minus, same formula for the little ellipse, it's going to be pi, but on the small ellipse, we went left and right 100, we went up and down 50. All right, so I'm not even going to my calculator here. I just know this is 12, 1, 2, 3 zeros pi minus 5,000 pi, which is going to equal 7,000 pi. And now I might go ahead and go to my calculator and see what is 7,000 times pi. I'm getting 21,991. What did it say? To the nearest yard. Okay, so I'll call it good there. So that's how much space there is in the stands. But really, that's not that important until you get to number 4, which kind of is like, oh yeah, I guess it would be important to know that area. It's because each seat in the stands is going to take up an average of 0.8 square yards. And then we've kind of averaged that out. That accounts for all the aisles and all the extra space and everything. But just the stands in general, then, we're trying to figure out what is the seating capacity. I have this much space, and each seat takes this much space. So that's less than 1 square yard. So my seating capacity is going to be even greater than what this is. This is a pretty big stadium. All right, so all we have to do is take our 21,991 and divide it by the 0.8. Okie doke. And so the seating capacity here would be 27,400, and I'll go ahead and just round that to 89 would be the seating capacity. All right. That's all I've got on that one. Okay, more of those tomorrow, so be here.